We brought an end to our earlier discussion by talking about general GARCH autoregressive conditional heteroscedasticity model, and we also talked about how we can estimate and test an autoregressive conditional heteroscedasticity model with logistic or LM with logistic regression. Now we intend to talk about the extension on our autoregressive conditional heteroscedasticity models. As we know, there has been a vast number of extensions to the ARCH models, and if we can recall, the general ARCH model was in page 5, where it looked like it was the variance was a function of alpha naught plus alpha j v square minus 1, where and v square minus I, and the order was from I to q. So q was the order of lagged squared returns included in the model. So that was, and the parameters to estimate was theta alpha naught to alpha q up until alpha q. So we're talking about lagged squared returns now. And so when we let's get down to the GARCH model, the univariate extension. Now, previously the ARCH-Q model has the property that the memory in the variance stopped at lag q. We suggested that the process for exhibiting long memory in the variance, it would be necessary to specify and estimate high dimensional models. So if we wanted higher orders in that model, we wanted to specify the model again. A natural way to circumvent this problem is to specify the conditional variance as a function of its own lag. So we're talking about, we talked about conditional and unconditional means and variances, and the conditional variance can be expressed as a function of its own lag, and this is the additional term that is being added to the basic equation, where, as we can see, besides the squared returns, the variance itself is a function of its own lag. Isn't it very simple? And the order of its own lags are up until p. So the equation becomes now this, which was previously the ARCH model alpha naught plus alpha I squared return up until order q plus function of its own lag. The conditional variance is being expressed as function of its own lag. Here the order is up until p, and this is known as the GARCH PQ model, where p and q identify the lags of the model, and g stands for the generalized ARCH. It stands for generalized ARCH. Once again, without loss of generality, it is convenient to work with GARCH 1-1 model, just like before, where y is equal to v because we have mean 0 and sigma square variance, and we're talking about variance here, right? So v is the equation of where the sigma square is represented with alpha I y square minus 1, just like before, plus beta I sigma square minus 1. So the squared returns are being presented with y. To highlight the memory properties of this model, using the lag operator, rewrite the expression for conditional variance. So we can rewrite, just take the right hand side stuff to left hand side, and we can rewrite 1 minus beta 1 L, okay, because beta 1 L sigma square equals sigma square, so that is a common factor. So 1 minus beta 1 L, we have taken the common factor, assuming beta 1 the factor beta 1 is less than 1, which is located within 0 to 1, and using the properties of, now what is the importance of having the value less than 1, because Well, it's coming from previous restrictions. If you can recall, we had to take the conditional for to estimate conditional variances. We had to take the values between see, an estimate theoretical unconditional variance and conditional variance all were below within the estimated results were within the under 1 for us to have consistency. Well, it's also usual to confine attention to cases in which process generating the disturbance is variance stationary, that is unconditional variance is unchanging over time. This requires that in the previous very basic equation where alpha naught is where we express in terms of the equation so when we express our variances in terms of alpha naught divided by 1 minus alpha 1 sigma square, so we are talking about unconditional variance here, alpha naught divided by 1 minus alpha 1. In terms of that, just hold on with me for a second here. So the unconditional variance is unchanging over time, so only this is possible to have a variance stationary disturbance if our alpha 1 is less than 1 in equation, which can also be imposed by using an appropriate transformation of the parameters, and where alpha is being expressed with the parameter delta I or being expressed with exponential of delta I, and later it can be replaced back to alpha I. So that's what significance, or that's what is significant when we keep our coefficient below 1. So here is also we are assuming our coefficient beta 1 to be less than 1, and using the properties of the lag operator, the conditional variance is now being expressed with, well, variance is being expressed with 1 minus beta 1 L inverse alpha naught. So we have first converted that to a lag operator. We took a common factor, then again we are going back to variance but with an improved specification, because now we are making this common factor a denominator for the right hand side equation. So alpha naught divided by 1 minus beta 1 L plus alpha 1 y square minus 1 divided by 1 minus beta 1 L. And how we so alpha naught multiplied to 1 minus beta 1 divided by 1 minus beta 1 L can be represented with alpha naught divided by 1 minus beta 1, which is simply a representation of alpha naught divided by 1 minus alpha 1 like before. So alpha naught divided by 1 minus beta 1 plus alpha 1 y square minus 1. This is we are removing the first bracket from here, and what do we have left? We have alpha 1. Well, this is another generalization of the model. We have alpha 1 beta 1 I y square minus 1 minus I. Simply speaking, let's just take it up there, and we have beta 1 I y square minus 1 minus I, and I is equal to 1 to infinity. So as you can see, this is instantly recognizable and arch infinity model. So is this model at all difficult? Not at all. So we are talking about a conditional variance model, where what did we do? We just introduced a new parameter, a new term, then we took a common factor, then we used the common factor as a denominator, and the first part of that equation represents the same unconditional variance that we're talking about. So instead of alpha 1 we have beta 1, then obviously alpha 1 y square minus 1, and then comes this portion minus beta 1 L, so y square divided by alpha 1 y square divided by beta 1 L. Instead of using the divided by beta 1 L, we can express that as beta 1 I y square minus 1 minus I. That's all, where I is equal to 1 to infinity, and that we can recognize as R's infinity model. The third term in the equation captures the effect of higher order lags. So we're not talking about higher order parameters, but we are talking about more lags. So y square minus 2, y square minus 3. So the third term is now capturing the effects of higher order lags on the conditional variance, which are now controlled by the parameter beta 1. Beautiful, right? So we have somehow in our system being able to introduce higher order lags. The GARCH model is therefore an attractive specification to use in modeling financial data because it provides a parsimonious representation of the memory characteristic commonly observed in the variances of financial returns. This sentence means that it is important for financial returns because higher order lags, the effect of higher order lags are being captured in the GARCH model. Another way to highlight the memory characteristic of the GARCH conditional variance is when we just simply define it as a forecast error. And how do you do that? Y square, we're representing variance as y square, so y square minus sigma square equals to the forecast error. If there was no forecast error, then remember we are representing our variance v equals y. So instead of that, we are just doing y square minus, which is the squared returns, the difference between the squared returns, the variance and the squared return. The difference between the actual return and the variance equals E is forecast error, which has the property of the E being 0 before. So there was no forecast error earlier in the lagged expectation or earlier expectation. Rearranging this expression, so let's rearrange the new expression where we have the forecast error represented as y square minus the conditional variance, or we can rewrite it in terms of y square. Y square is the squared residual, squared returns. Y square equals sigma square plus et conditional variance. Now just put the whole value for conditional variance. So alpha naught plus alpha 1 y square minus 1 plus beta 1 y square sigma square minus 1 plus et. Now what can we do? Sigma square is there. Okay, because you see sigma square can be represented with y square minus et. Sigma square minus 1 might be represented with y square minus 1 minus et minus 1. So yeah, that's just jack that idea inside here, y square minus 1 minus et minus 1, and then we have another equation. Now remove the brackets, and if you remove the brackets you have a common factor, alpha 1 minus beta 1, alpha 1 plus beta 1 y square minus 1 minus beta 1 is common. So we rearranged. So it's very simple. We had a forecast error, we rearranged. We put the values of the GARCH specification, and after we have done that, we thought it a bit further to introduce one more lag. So we are seeing how the recursion is happening. The recursion is actually appearing inside the body of variance sigma square minus 1, which is again equals to y square minus et, which is an ARMA 1-1 model. Beautiful. Now we have an ARMA 1-1 model from GARCH specification. So we have an actual forecastable model in terms of y square. So they are being represented in terms of y square. So we stick to we are sticking the representation to y square, and we have a GARCH one ARMA model, which is a forecastable model. The memory of this process is determined by the autoregressive AR parameters alpha 1 plus beta 1. Okay, so this represents the memory of the autoregressive parameters. The closer alpha 1 plus beta 1 is to 1, the longer the effect of shock on volatility. Beautiful line, right? So which will mean if it gets to closer to 1, there is higher effect on volatility. The effect of a shock on volatility in the long run. So in the long run, the effect of shock on the volatility is captured with unconditional variance yt, which is defined as sigma, which is defined as the variance. Taking unconditional expectations, long run is obtained from unconditional variance, okay, defined as sigma square. Fine, we have no problem defining it as sigma square. Taking the unconditional expectation and using that unconditional expectation, et equals, depending on and the expectation earlier was for the forecaster was 0. It follows. So now we are focusing on the forecast error, and unconditional expectation of forecast error in the earlier period, the past period, was 0. Indeed, there was no forecast error, it converged. So we have what? Let's take an unconditional expectation of y square, which is now the equation that we have just talked about, the ARMA model. So alpha 1 plus beta 1 y square minus beta 1 et minus 1 plus et. We just take that, jack that in, and unconditional expectation of y, unconditional variance of y square is represented with unconditional variance y square, right? Equals alpha naught remains alpha naught plus alpha 1 beta 1 remains alpha 1 beta 1. Y square minus 1 is also the variance, but the earlier expectation of the forecast error becomes 0. Expectation of forecast error becomes 0 because we're taking expectation, so there is no forecast error. That whole term becomes 0, and when that whole term becomes 0, we're left with y square minus 1, which we can represent as variance in the common term, and we can rearrange just like before the variance, which will give us alpha naught divided by 1 minus alpha 1 plus beta 1 in bracket. Same thing, right? So the unconditional variance in the long run becomes sigma square. So we had always talking about, we were very well talking about short run and long run variances. So what did we do? First we specified very quickly, our arch into GARCH by including this new variance own lag of the conditional variance itself. Then we took that idea, took it a bit forward, because then because there is a common factor, we have taken the right hand side stuff to left hand side, took a common factor, then again we used the common factor as a denominator, and when we use that a denominator for the right hand side, we found that the first element can be represented with unconditional variance, then the second element remains just the same item when we remove the bracket, but the third element captures the long run effect. That captures the effect of higher order lags. It captures the effects of higher order lags y square minus 1 minus I up until I. It's because it's an infinite order GARCH model, infinite order arch model. And then to control filter for the memory characteristic, we have learned that we can determine our forecast error, and we take the forecast error equation because one element of the forecast error equation is our y square. So we represent the forecast error equation with y square, and we find that, and we have a value, we have a specification for the conditional variance. We put that in. When we put that in, we also remember that the same forecast error can be represented for its lag. So we take that information, we jack that into the third element in terms of the forecast error equation, and then we remove the bracket, take the common factor, and we see we have an ARMA 1-1 model, or a forecastable model. And we learned that the second element, alpha 1 plus beta 1, as it is closing to 1, that means the effect of shock will be longer. Keeping that in mind, now we generalize. We take expectations, and when we take expectations, we don't have any forecast error, because forecast error completely removes when we take errors, remove impact from past information is removed when we take expectations. It's perfect, right, in expectations. And we have a generalized unconditional variance equation. okay, which is alpha naught over 1 minus alpha 1 beta 1. So beautiful. Now we have a GARCH model with which giving us a conditional variance and unconditional variance equation. Example: autocorrelation function of a GARCH-1 model. The autocorrelation function of the GARCH model is simulated for, this is an example we will probably do for 1000 observations, and we do a short and a long memory, short memory and a long memory practice, where the memory classification is determined by the size of beta 1. See, long memory has higher beta 1, short memory has smaller beta 1. So the ACFs are also given, autocorrelation functions are also given in figure 20.4. the first model and the second model, one is the short, one is the long GARCH-1 model. So this is the short GARCH-1 model, is more non-linear. The long run GARCH-1 model is impact of shock is just one time, whereas impact of shock is a bit different here, right? So in the short run the decay is faster, that is what it means, where in long run the decay is basically slower. Oh yeah, see, the decay is slower and it decayed quickly. So the shock has been absorbed by the variance quickly in the short run, where it takes a long time for the long run. As with GARCH model, the GARCH model can be estimated. So however, now we are gonna estimate just like GARCH. We're gonna use maximum likelihood function using the gradient algorithm. For GARCH-1 model, parameters are alpha naught, alpha 1 and beta 1, and the log likelihood function is first half factors y plus sigma square minus half y square by sigma square. Okay, so we have the variance instead of the variance sigma square. We put GARCH equation in both of the sigma square place. That's all, very simple. In the estimation, as with GARCH, it may be necessary to restrict alpha naught, alpha 1 and beta 1 to be positive in order to ensure that the conditional variance is positive for all time t. Beautiful. The Euler-Walden LM testing method can also be used to test for GARCH model. The LM test derived previously in the context of GARCH model is still relevant, so we're still finding some relevance with the GARCH model. It should be noted that finding GARCH at relatively longer lags. So okay, so when we are even finding GARCH at a longer lag, which means a GARCH-1 or GARCH-2 model is presented there when our GARCH even gets bigger. So natural test is to test for beta 1. If there is beta 1, that is GARCH. If there is no beta 1, this is not GARCH, which may be implemented. So generalized GARCH is GARCH, which means simply the presence of the impact from the lag of conditional variance itself on itself. When the conditional variance itself becomes a function of itself, that becomes GARCH. That's very simple. It's not necessarily, because in an GARCH model we don't have the conditional variance as a function of itself, so it's not forecastable if we are using GARCH. But we know in GARCH we are just dealing with squared returns. So let's talk about GARCH model of equity returns. Good. So there is a table 20.2 which contains the maximum likelihood estimation results from 3 different indexes: alpha naught, alpha 1 and beta 1. So what does it mean? An important feature of the results of GARCH-01 or GARCH-1 model are also given. Okay, so this is GARCH-1 model's result with standard errors, and this is GARCH-01. No lags with GARCH. 0 Q is 0. So 0 1, this is GARCH-01, and this is for comparison. and this is R with standard errors. Okay, so let's see. Standard errors are estimated from Hessian. As we know, if we solve the problem, we can easily find gradient and Hessian. An important feature of the empirical results is the consistency of the parameter estimates across all three equity returns, with the estimates of beta 1 being around 0.9. So estimates of beta 1 is 0.9 in all three. Wow. 0.9 in all three estimates of alpha 1, and estimates of alpha 1 being 0.05 to 0.1. That is also an important finding. 0.05 to 0.1 alpha 1. So beta 1 has a limited range, alpha 1 also has a limited range. Table are the theoretical variance computed using equation also given in table 20.2 are the theoretical variances or unconditional variances computed using equation 20.30. Let's see what 20.30 equation was, right? This is page 15. 20.30 equation was this one, the unconditional variance equation. So that is also presented. Also again, theoretical variance computed using equation 20.30, and this is the theoretical variance and this is the regular GARCH variance. There's good agreement between these two statistics for all indexes and all models, with the exception of Nikkei in the case of GARCH 1.1 model. So in GARCH 1.1 model, only the theoretical and empirical deviates. Okay, so the theoretical is much higher compared to the regular. Then we are talking about another figure, 20.5. Figure 20.5, conditional variance estimates of zero mean percentage daily returns. Zero mean percentage daily returns. So what does that mean? Which means that figure 24 is plot of estimated conditional variance of FTSE. So GARCH estimated with a rolling sample. Okay, estimated conditional variance. So we have a vector of GARCH. So we did a rolling over there, and the first three observations of H are computed recursively as the first observation is y square divided by t, the simple variance, because we need to initialize somewhere and we are initializing with the actual variance. We studied that before. Then it goes on based on our function. Okay, so we have a vector of GARCH. Here y1 and y2 are the first two observations of the zero mean returns. So zero mean and variance, we are thinking mean as 0. In the case of FTSE, in the previous table, we found a log theta is for GARCH 1.1 model and for ARCH model. So the likelihood function is a bit different. So LR statistics is simply 950, which is distributed as chi-square null. The p-value is 0, indicating a strong rejection of ARCH 1 model at 5% in favor of GARCH. So in the system, GARCH exists. We don't have ARCH, we probably have GARCH in the system. So ARCH is rejected in the system. That's what is being meant here. Very simple. So we do LR statistics. We take a log likelihood for GARCH and we find obviously the system gives us the log likelihood for GARCH and ARCH, and we just compare that. It's very simple. Beautiful. Then we can talk about integrated GARCH. But I need to pause it a little bit. Yeah, where is it being recorded? So let's pause it. So whatever we learned up until now, we're gonna quickly put that into action to some extent. Let's see how we do some of the ARCH and GARCH estimations. We have seen 2 exercises. We're gonna look into 2 more exercises, right? So third problem, we are to simulate a GARCH 1-1 model with this equation. However, simulation is not necessary. We can try and find if a GARCH 1-1 exists in our current data, which is the regular thing to do. But let's just simulate a GARCH model just for the sake of, fun. For a sample size of 100,000, we're going to use this given parameters, and obviously there will be a starting value in our simulation, and we'll start with the unconditional variance y alpha naught 1 minus alpha 1 minus beta 1, and variance will be 1 minus alpha 1 minus beta 1. So that is what we already know from unconditional distribution and unconditional variance. And then we need to find the autocorrelation function of the variance, compute the results, and we're gonna change our alphas again, see what happens, and yeah. So we were gonna compare which one is ARCH and which one is GARCH. That's GARCH simulate problem. Let's see our GARCH simulate problem. First of all, to notice there is one function. There is just one function, autocorrelation function for p lag, the order p. Order p is our GARCH order, or the order of the higher order lags of the conditional variance. So p, autocorrelation function has the input and the lag. So d is x minus mean of x, and we use d because what do we find? We find r, which is dp0 multiplied to d0, which is simply yt multiplied to yt minus 1, because remember the equation summation of y squared divided by t. That's what we are trying to do, divided by sum of the x minus mu x. That's all. Y squared divided by x minus mean of x squared. Okay, so x minus mu x, the variance squared. So that is our correlation function. That is the very simple distribution we always do, y squared divided by x minus mean of x squared. And we're gonna just jack that in R is the same thing. We just need to load for trim R and for figures these R function, and then yeah, this R, and then if we have we don't need any function in R because autocorrelation function is an internal function already set in R. I'm gonna skip this Marciana twister part. I've been going through it for quite a long time, so we already know how we simulate. So we're gonna simulate with 100,000 data, and the maximum lag will be 20. I mean the higher order lags. So first we need Z, which is, we're gonna use Z because random number of Z is generated for 1000 extra, which will reduce later. Rows and one column. U equals Z, our residual. Y equals Z because Y equals what? U square. Y square equals U square, so Y equals V actually. H is our model, right? So we're gonna represent our model with ones. Ones will be number of observations plus 1000 extra for one row. Now in R it's replicate 1. The function is replicate 1 this number of times. So we input our given parameters. Then H is our unconditional variance. So the first element of H is given, which is, remember that alpha naught divided 1 minus alpha 1 minus beta 1, exactly that. A naught 1 minus alpha 1 minus beta 1 is the first one, and for the first one the residual U. The error is also estimated because we need y minus, remember the relationship between forecast, then error, E, then we have y, then we have ye and sigma. That relationship is very important, the variance ye and sigma. So u is normally generated here. U means the whole, zero mean variance. The zero mean variance is 0 and the variance, which is simply h. So we generate it. Oh, fine. See, that's what they do, square root of h1, normal random. So r norm 1, r norm or normal random, or r norm, again normal random and r norm in r the same, or r norm, one vector, we want just one vector, zero mean and square root of h variance, normal random, r norm, zero mean and square root of h variance. Generate data. Now let's generate the data. Progress bar not necessary. So t is equal to 2 to number of observation plus 1000 for that number of cells. We estimate our conditional variance, 1 u t minus 1 u t minus 1 square. U has been already found as zero mean and conditional variance. So 46. Let's have a look into 15. So zero mean and conditional variance, let's have a look into that. Let's see where we can find that zero mean and conditional variance in our GARCH models or ARCH models. It's somewhere. Right now I cannot. So no, this is the equation, log likelihood equation. So here is, as we know, long run variances. So zero mean and long run variance, the whole thing here, right? Zero mean, the effect of shock. We are finding the effect of shock. Zero mean and long run variance. So u is equal to okay, a1 ut minus b1 ht minus, so sigma square, and this one is what? One is sigma square and the other one is the regular. Let's go back to our regular model, y square, or v square or u square, right? The same thing. Okay. So v square and sigma square, where v square is z multiplied to square root of h, z square root of h, that is our error generalized. So okay, here we are using the square root of h. So this will be generate this many times, this will be generate this many times, y equals u. Okay, y equals u. So we have h, we have u, we have the GARCH, and y equals u, right? Yeah, that's the very basic that we learned. Z divided by root over. So z is equal to where is equal to since under the null hypothesis 0 y, so z, here is z y divided z multiplied to the alpha naught square root of h. This is h, sigma variance, right? Sigma variance. So this is sigma z square root of h, z square root of h, and y equals z square root of h. This is the equation. Wow, yeah, this is the equation, z square root of h, y square, and that's what we did, z square root of h and y equals. So we have y and we have h. So we trim y because we are looking for y, and to find y we needed the GARCH model. So this is your GARCH conditional variance, which has been square rooted. That's the equation. So the conditional variance is square rooted multiplied to z distribution, and then z is simply random normal distribution. Y, you have y. Z has 0 mean and 1 variance. Okay, so this is generalizing, because the RNDN, random number, generates number between 0 to 1, so it doesn't go beyond that. So R norm generates number between 0 to 1, or here is another R norm somewhere. Yeah, so normal random 0 to 1, maximum number of 1. So this here u1 is the first one, just the first one. Then z square root of h equation is used, and then we have y, and we can take the y equals take the difference. Okay, so compute the autocorrelation function is simply do a looping again up to lag j. So we have ACF j plus 1 is, we run the function on y square and j. So our function required x and p. So x is y square, obviously the variance squared, y equals v, here the variance squared, up to j lags, that's all. And that is done for 0 to 20. So we have 0 to number of lags, so number of lags is estimated. So that is the model. Quite simple model, there is no complication in this, you see, and we have been able to practice, revise our stuff. So this is again the same thing for the second autocorrelation function, just with changed alphas, that's all. And then we generate the graph, and we get the same graph as short and long run graph. So we saw the graph results when you have a short run element or shocks in the theory. So what did we have? Remember, just have a quick look. Let's just have a quick look. Yeah, so autocorrelation function suggests that two GARCH models, the first model, the second model, has parameters this. So with this, what did we find? In the first model, the short memory feature of model 1 is highlighted, where in the longer memory the decay is slower. So there is a difference between the decays. So we have the short memory, we have the long memory. The memory relative size of, so memory classification is determined by relative size of beta 1. So because of the difference in beta 1, the decay, the speed of decay or speed of adjustment is different. So that's what it is done here as well. There is no trick, we can do it. Okay, autocorrelation function is simply in R, is easily estimated. We did not have to declare any correlation function, so we just simply put x, number of lags, for number of lags, and it also does plotting. Okay, and we take the ACF part of the analysis of the outputs, only the ACF is taken out. So plotting is false, we don't need the plotting for now. Then we can do it ourselves, generate the graphs ourselves. That's the plan. Alright, beautiful. Then comes GARCH equity. GARCH equity, and see how GARCH equity works. The next problem is suggestive of estimating a GARCH model of equity returns. The exercise is based on the same data that we have used. So there is a data there. Now we're going to use the data, no simulation. Previously, practically the first model was quite easy, but the zero mean percentage return is used. So percentage return is not generalized. Okay, so plot the conditional variance and interpret the in-series pattern. Compare the quasi-maximum likelihood standard errors assuming heteroscedasticity with the standard errors based on Hessian and outer product of gradients. Okay, so we want to look into quasi-maximum likelihood standard errors assuming that they are heteroscedastic. So we're gonna find the conditional and unconditional variances. We're gonna test a GARCH model against an ARCH model, and then there is a iGARCH model, but we're not gonna do it iGARCH now. So let's try with GARCH on our data, and let's see how that is done. Is there any local function? Indeed, there will be local functions. First of all, let's have a look into all the local functions. First of all, we do a wrapper function for GARCH. To begin with, we do a wrapper function for GARCH, log, neg log, mean, log LT, by, generally what we do. Then the log likelihood function for GARCH. One is we have b, absolute value of b, t, absolute value of b is taken, then t is equal to length of y, u equals y, okay, h equals y square, standard deviation of y square, right? Standard deviation of y square multiplied to 1 t, because we're gonna put a loop on. This is the GARCH. So first, standard deviation of y square multiplied to 1. We're gonna put a loop over them. So for result 2 to t, so this is the one, the first one, t rows column 1. So this is the first one. The rest will be replaced. Y square once t rows 1 column. The variance, this is the first variance, regular variance. Okay, standard deviation of y square means regular variance. Y equals by. So from 2 to t, this is the regular GARCH model. U I minus 1, we need u I minus 1 square, because u is 1 is the variance sigma square, 1 is v square or y square, right? V square. So v square, regular v square or y square, they're the same. So I minus 1, and then log likelihood function. This is for 2 to t. This is the equation. After that equation, whatever h is derived, we're going to use the h for a log likelihood function. Half log twice y, half log in place of sigma square, because this is conditional variance sigma square. Anyway, we're deriving the conditional variance. Half log u square root of h square, u divided by y divided by square root of h square. So we already know y square divided by sigma square, that's all. Okay, for the ARCH model, again neg log function of b lag y, mean of log likelihood b y. Always we have done that, and then we want the system to return log L when if you call for log neg log. Log LT will return GARCH 1 model. Absolute value be t, length will be length of y, u is y because u is v square, uv, and standard deviation y square. Replicate 1, multiply to replication of 1 t times, just so that we have the initialization. A squared u square u minus 1. So this is the equation, and then this variance we use for our log likelihood function. Then ARCH model is the same thing, log likelihood log LT. When we call for log LT, we want this to derive give us ARCH model. Same thing, same, just in the equation the third element is missing. We put that in iGARCH. iGARCH we haven't studied yet, so we'll just keep it as it is. Then we're gonna use it for our first data set. We're gonna load equity. I'm gonna take the first, just the first data. I'm just gonna take the first data. In R, we want to read our table as matrix. We want to convert everything into matrix. Okay, you could have just read the table and do that in matrix instead of going through all this trouble, and take the first data. Then we take the return log equity, so log returns are taken, and then the difference is taken, so that we can easily generalize the data, because we want our values to be within 0 to 1, and that's how generalization is being done. Then length is taken. Then we have what? Estimate the GARCH 1 model. Options is start. We're gonna start with some random values, 0.05, 0.1, 0.9 alphas given to us, right? Is there in alphas given to us? 0.05, 0.1. I don't think there is an alphas given to us. 0.1, 0.9, just random numbers. So start, we create a column to start with. See, optimal last scale of displayer. Then theta, we want theta, log likelihood function, and Hessian because we want to find standard errors. At B, fn in B, neg log by start ops. Here it's very simple. It's an optim start optim, then take the par value, initial value, then neg log, call the function neg log y equals y, method vfgs Hessian true, y equals y. So at B, neg log by comma start comma ops. That's the optimization function. So LF1, so we have theta estimated for estimate. So theta is the par value, initial value has been replaced with theta estimates. Then we have log likelihood function and Hessian. Okay, and take the negative values of the log likelihood function. So we have what? GARCH 1 results alpha naught, alpha 1, beta 1, log likelihood function. Very simple. Now let's do at optimal parameters. We have optimal parameters now. We first, what we did we had optimal parameters? No, we just passed some equation, and with some initialization of parameters we estimated something. Now with optimum parameters we estimate our GARCH model one more time. Okay, so whatever number was there for theta 1, theta 2, theta 3, that has been replaced in our GARCH 1 model now. So we have again H equals, the GARCH model is standard regular variance, U is equal to y minus theta 1 alpha 1. So obviously E equals y square minus variance, y minus theta 1. So U equals y minus theta 1, the forecast error, right? Y to theta 1 difference. Okay, fine. And then we can draw the graph and we will see our GARCH model being plotted. And how did it look? It looked like something like this, right? So we had our GARCH model from there. Okay, and after the figure comes standard errors, comparison of standard. So Hessian inverse is taken, square root of diagonal Hessian, square root of diagonal elements from the Hessian is taken, diagonal elements of the Hessian where the standard errors are located, and then gradient is also calculated, estimated. Gradient is numgrad at log LT theta transpose y. Numgrad log LT for GARCH model theta y. Okay, fine. So gradient is found. So up until this point we have standard errors, then gradient is found, then J, the outer product gradient, is also found. So this is theta. For theta is all the parameters, right? Oh, so all parameters, for all parameters. Okay, so all parameters are passed into gradient. Obviously that is done, 0, alpha 1, alpha 2, that's how it is done. And outer product gradient is found, and again a new standard error is the same equation. The sequence is, and then we have is EQ, Hessian OPG QMLE. I'm not sure what QMLE is. Maximum likelihood estimator. Okay, whatever. So a variance decomposition is taken here. A variance decomposition is taken in SEQ. So standard errors, we have different standard errors. That's what it is trying to mean. And then comes GARCH model. Now it's restricted because the same thing is repeated but removing something at the end. And then we take the difference to find log likelihood ratio, and from and present value of the log likelihood ratio, p chi-square CDF or p chi-square, which should suggest if we reject the null of GARCH or GARCH. So that's the part. Then we're gonna start talking about iGARCH, but now up until this we record whatever we learned. Thank you.